Hi, this is Jeremy Colmel, research faculty at Yale University and CEO of Innovative Omics. In this tutorial, we get to cover the fun part, which is looking through the visualizer, taking all the evidence together to try to identify polymers. You can see the non-targeted analysis videos. We'll go over each one of these plots in depth, describing the mathematics behind them, the basic principles, so you can get a strong idea for what each of these plots are, because we're only going to briefly discuss those here. So the first plot here is a Kendrick mass defect plot once you load your data in, and this is going to have your homologous series. So for example, on the bottom here we have some polysorbate with a PEG. Here we just have a PEG, and you can see that the units of the PEG are going to go down each time we go to the left because we're normalized, unlike lipids where we're normalized to CH2 or PFAS where we're normalized to CF2. In this case, we're normalized to the CH2CH2O repeating unit. And so everything's going to be separated by the mass of CH2CH2O on the x-axis, and in the y-axis it's going to have the same mass defect if it's the same polymer subclass, such as PEGs will all fall in one line, PEGs with a fatty acid 16O will all fall in another line, PEGs with a fatty acid 18-1 would all fall in another line, etc. So these lines give us the subclass of the polysorbate, or PEG or other polymer. Now on this plot over here, it's a retention time versus mass to charge. So if I select, any one of these series, so let's start with the PEGs, right? So I can shift select down, or I can select the specific series. So let's just select down. Better to choose one series because we got two here. So let's see, 482 is the series number. So I can look 482. And now you can see this nice trend line for the PEGs that makes sense, and you can see the false positives over here, and you could easily confirm the compounds that are here. There are two that look like they have isomers. So we can look over here. It doesn't look like there are isomers actually. And it looks like this is just a peak picking issue where it picked the peak twice. So in those kind of cases, then we can just say that these are the true species. For the PEG, and everything else is a false positive. Now note that when you open, usually depending on the version, this is already filtered by score. You can take off this filter in case there's anything else that may appear that has a different score, so make sure to take off that filter. Now you can see the nice trend line for the PEGs. You can see their MS1, you can see their MS2 spectra over here, which should have all the PEG fragments, as you can see, plus the precursor masses. If we select any one of these, let's see what we've got here. Looking for one that may we can see the formula prediction algorithm over here and the MS1 isotopic profile over here. The MS1 isotopic profile is going to be more useful. These are extras. Just using the MS and these trend lines alone, you can be pretty confident in these series, or highly confident, especially when you're getting all these pegylated fragments, which we can scroll over to show. So this would be it's not. The C4H9O2, C6, and C8, and so on and so forth. And then this is the precursor mass. And so we can be very confident in this PEG species. It's got the right fragmentation, it has the right trend line and retention time. All these other ones are false positives. We can throw them out. We can also look at the MS1 spectra. If you look at the C13, it gives you the theoretical abundance, which is 1.08%. And this formula is C12, so we'd expect about a 12%. Indeed, okay, 50 is about, give or take, 12% of 400. So it's within the right range. That's the important part, right? And then you can also see the C13-2, what it should be, about 0.01%. So that 0.01% times 12 would be about 1%, 1.2%. So here it is, and so on and so forth. And so now we can see where that the theoretical versus the actual is, but in this case, it's not actually the formula is not actually correct. In the next version, it will make sure to include the formulas that were identified so you can see how the theoretical versus actual match. But just know that the formula prediction at this point is not very accurate for most species. We will show you some matches that are correct and walk you through that. So when we want to annotate our compounds, we've now seen all of these different pieces of evidence we can use. We're going to open up our table. And here we have, let's go and freeze frames. There we go. So now we can scroll through. And the other thing is I hid a bunch of cells. So in this, if you right click and hide the columns so that we can just see the row ID is the most important. And then this series is going to be very important. And then the check and true. And these are where we're going to annotate our compounds. So in this case, it starts with series 405. So you can just go by series in that way. So let's go to series 405. Unselect this one. All right, so here we have a very nice series. Almost no false positives. And this is, if we scroll through, we'll find a structure because all the A's have a structure. It can be very hard to see the structures for the large ones, so often I start at the low ones to get an idea for the structure. Okay, so it's a polysorbate with a PEG on it. That's all. Forms a very nice trend line. These we can all confirm as true. This one at the end has also got an A, so it has the correct MSMS spectra. It's got your pegylated units. And so I would also consider this one true. You can see that the fragment profile matches neatly. So everything's going to be true. So in that case, all we have to do is go check as 1, true as 1, drag these down for the entire set. Now let's move on to 579. And that's how we're just going to move series by series to annotate these compounds to confirm. So in this case, a little confusing. We do have quite a number of series here. These may be isomers, they could be oxidized species. Not exactly sure in this case. If we only select our A scores, so our confident ones, B pluses are going to be fairly confident as well. There we go. So we do have this one series really over here. And so when we add our C pluses in, we can know which series that is. So one way I'll do that is I'll just select this one. Okay, do these have our A's in them? No. So this must be some other compound. It doesn't have any MSMS, so we actually not sure that it can't just be an isomer. And then let's select this bottom series over here. Does this one have our A's in it? Nope, this one's all C+2. So it looks like the only series, these are polymer series, clearly, or at least these two. This one, the retention time behaves a little strange because it doesn't move with retention time. So this is going to be our series that is correctly annotated, at least. Doesn't mean the other ones are not series, they're just potentially not the right annotation. Here you can see the nice series. And here you can see all the high scores for these compounds. So I did want to show an example of a case that's correctly annotated. So in this case, the formula is C44H84O17. So we have C44H87NO17. Now, this is due to NH4 adduct. Also, the reported species are for an M plus H. And so it actually has, so this is, if you did M plus NH3, because it already has an extra H, to that formula, you get the same formula. So just something to be aware is that this formula assumes an M plus H and predicts off the ion mass, knowing nothing about the adducts. And so you will need to back calculate if you know what the adducts, and if you don't know the adducts, this is not the formula of the molecule, this is the formula of the adduct plus the hydrogen. So just to be aware of that. All right, so this would be the correct series, and then just as in all our other applications, we're going to highlight these series, go in here, let's move this slightly over so we can now look at the table, and this table is only going to show what we've highlighted, and so now we know the features that are true here, and we can mark those here as well. So I'm going to drag this down again for 579. And then let's look for, so 1566 is our first one, then 1569, then 1612, then 1646. So one thing we might want to do is sort by MZ, because this is also sorted by MZ or retention time, and that will be a little helpful for us to have the same order. So now we can start at the beginning, 1398, 1433, 1474, 1522, and then we've got our 1566, 1569, 1612, 1646, and 1649, and 1673, 1706, 1742, and something. All right, so now these are selected in. Now I can save this document. You always want to save it as a new name. One, you just don't want to overwrite the original document, but also when you upload it into the visualizer, it always has to be a new name or it won't update. Or you can change the directory, either one of those things. All right, so now I've uploaded it. I've saved it, and we can upload the new data set. Going to data source settings, we're going to change this pos ID'd fin to pos ID'd fin annotated. Press OK, close, and apply changes here. And once those changes are applied, the dataset should look exactly the same. The only difference is now that we can use these annotated columns to filter by, so we can look at just the compounds that we had annotated. Alright, so we're loaded in. And now if I go to checked, you could see one is it's checked, NA is it's not checked. In this case, all of them were checked, right? Because we looked at the series. And then flag, NA, we left. One we left as annotated. Now, you can put whatever you want here. You could put a 0, 1, 0.5, yes, no, maybe. So you can use words, numbers for how you want to flag your compound. So it's really up to you. You can create your own rubric. For now, we just used one as confirmed in here. Now you can see your confirmed species. If I take off my series, we can see the two confirmed homologous series, and obviously we could continue going on from there. Let's unselect our scores and also unselect our flags. Now, if you unselect everything, unfilter everything, it's going to potentially lag a little bit, especially for other types of computers. We have a very high performance computer we're running this on. So that would be how you'd move through your table, series by series. You would move until you get past molecules that have B pluses or A's in your table. At that point, there might not be very confident species, and you can stop there, or you could continue. Now, once you've annotated everything from the top to the bottom of your table, given that the top is the most confident series, and so on and so forth, eventually you're going to get to the point where you're not going to use the table anymore to discover new compounds, but you can use other techniques. So in this case, assuming you've uploaded the latest annotated file, I would go into NA, which is going to remove those that have already been checked, right? Because we're only looking for new series. In this case, there weren't many that were checked, but eventually you would have a lot. And then let's say I want to see all my fatty acid species. So I can look at a fatty acid fragment here, click it. I can also use an intensity cutoff. Let's say 2000 to make sure that we have a high intensity fragment. And here we can see quite a lot of the species have still been retained. Some of these, like this PEG with the R2 fatty acid 18-1, 18-1, makes sense, right? So these have the 18-1 fatty acid. These would have already been annotated. You might also end up with species. So here's a lot of annotated species, actually. Such as, let's see if any of these series. So these are still annotated. All right, so this 725, for example, looks like a trend. Same thing for this light blue one. So this is going to be 528, series 528. So if I go to series 528, I can pull that series together. Now, make sure to drag this to 0 and unclick something to see an entire series. So here now we can see the nice series over here. So this is an unknown series, but it does have quite a high fatty acid for 18:2 fragments, as well as the pegylated fragments and some other fatty acid fragments as well in the series. So this is probably a series of interest that doesn't have an identification. So this is where you can start your unknown identification. So another way to filter is by using the number in series. So if I select, for example, 19, then all of a sudden I'll get those that have the most members in the series. And this can be helpful for discovering unknowns as well. So I clicked 19. You can see some false positives out here, but you can see a very nice trend line This is definitely a homologous series for pegylated units. You can also see the pegylated fragments for some of these compounds. And if we scroll down, and the nice EICs, that polymer distribution right there. Same thing we can see in the MS1 profile. And you can see that these were all scored D+, so these wouldn't have been annotated. And so we may have missed these, but now because we're looking at those that have the highest number in the series and we can move in that direction, we can identify some of these unknowns as well. So another way to find unknowns. Here's another plot. Ignore this plot generally. This is based on mass defect. I just wanted to, versus the carbon number, which is gotten from the N+1, and the mass to charge versus the carbon number. So you do see this trend line though, which is really nice. So here's a PEG N13. And if you look at the retention time for these molecules, they're constantly going up. So these are for the different masses. So you can actually, based on these mass defect plots also, and their mass to charge versus equivalent carbon number, also see trends of homologous series. So haven't looked into that deeply, but something that you might want to investigate. So that kind of summarizes the unknowns analysis. You can also, if you're looking for chlorinated or sulfur containing or a certain carbon-13 ratio, you could filter by isotopes. You can look up a specific molecule based on its retention time and mass in case something you're expecting to find. We talked about using fragment screening. And so these are all ways of finding unknowns. And so I hope you enjoyed this tutorial. And looking forward to hearing from you. If you have some great data sets, please do upload them. innovativoomics.com. And you can go to datasets. And there you'll find different data sets, but we can also load yours, cite them, give the journal article, any links to your websites, etc. And people can look and have your live interactive data sets that they can go through. So, there's already some for polymers, lipids, and PFAS. So please send us your data sets if you want them to be open source in this format. Also, and we'll host them for you. Also, feel free to leave comments on this video or reach out as us at innovativoomics.com. Check out our services, our other software, our data sets, and different articles that we send out, and YouTube tutorials, all available over here. Okay, with that, I'd like to thank you.